Welcome back. In this lecture, we shall solve an example of a propped cantilever beam with an internal hinge for the analysis of shear force and bending moment at various sections along the beam length. We draw a propped cantilever beam with the left end fixed and a roller support at some distance inwards from the free end. Let's label the key points as A, B, C, and D respectively. The lengths of various parts are dimensioned and the loadings acting on the beam are also shown. The beam is made up of two parts, AB and BD, with an internal hinge or bending moment release provided at the junction B. It can be seen that the given beam structure has a total of 4 unknowns, 3 for the fixed support and 1 for the roller support, while we have 3 equations of static equilibrium, making the structure statically indeterminate with the degree of indeterminacy as 4 minus 3, which is 1. To make the beam statically determinate, the additional deficient equation can be incorporated via the inclusion of the internal hinge at point B, joining the two parts of the beam. That is, the moment at the internal hinge equals 0. Let's break the beam into two parts at the internal hinge and draw them separately, showing the shear force transferred at B on either part due to the other part and denote it as V kilonewtons. Note that this shear force is shown in opposite directions at B on each part separately. Now for beam BD, we first find the unknowns at the points B and C considering static equilibrium. Analyzing the equations, we find that the reaction at C equals 250 kilonewtons and the shear force at B, that is V, equals 50 kilonewtons and is found to act upwards. For beam AB, the shear force at B, that is V, is shown acting downwards. Though the reaction forces and moment at A are not required to be found out, if we take reference as and B for finding shear force and bending moment equations, we still find them and show them on the schematic diagram. We begin writing the equations for shear force and bending moment for the beam BD, for which end B is taken as the reference. Now the distance x is greater than or equal to 0 and less than or equal to 10 meters, for which the shear force at x equals plus 50 minus 20 times x, which is linear with respect to x. The bending moment at x equals plus 50 times x minus 20 times x squared over 2, which is parabolic with respect to x. The double derivative of the bending moment equation is found to be negative and hence the locus curve over this region is of a maxima type. For region CD, for which x is greater than or equal to 10 and less than or equal to 15 meters, the shear force at x equals plus 50 minus 20 times 10 plus 250, which equals plus 100 kilonewtons and is a constant. The bending moment at x equals plus 50 times x plus 250 times x minus 10 minus 20 times 10 times x minus 5, and this equation is found to be linear with respect to x. The shear force values are plotted in the shear force diagram for part BD. We mark the location where the shear force is 0 as point E and is found to occur at 2.5 meters from the reference end B. The bending moment is found to be maximum of sagging type for this part with a value of 62.5 kilonewton meter, while for point C the bending moment is found to be maximum of hogging type with a value of 500 kilonewton meter. We plot a parabolic curve for bending moment for the region between B and C. The point of contraflexure or inflection is marked as F and is found to occur at 5 meters from point B. Now for beam AB, we consider the end B as reference from where the distance of imaginary cross-section, that is x, is measured. The shear force at x equals plus 50 kilonewtons and is a constant. The bending moment at x equals minus 50 times x and is linear with respect to x. We plot the values for the region in the shear force diagram and bending moment diagram accordingly. In the next lecture, we shall consider another solved problem and estimate the shear force and bending moment values along the length for a very long beam separated by two internal hinges.